topic today is we're returning to our favorite thing, which is finding a marker that works. So we're going back to bifurcations, and we're just, for the first part, we're just repeating everything we did in the previous lecture, except we're adding one dimension, where we did bifurcations in 1D, and now we're doing bifurcations in 2D. But for the first half of the lecture, there's no difference whatsoever. All right, so let's start with our friend, the saddle node bifurcation. In 1D, it was x dot equals mu minus x. What is it? Paper. Yes, minus x squared. That was that classic saddle node bifurcation. And what happened is you went from 0 solutions, 0 fixed points for x less than, for mu less than 0, and then there are 2 solutions for mu greater than 0 at plus and minus the square root of mu. Right? That was the story in 1D. Now all we're going to do is add a second dimension. And the second dimension, in our case, we're going to make it trivial so we can do the math. Right? So now let's just, so what happens? Now we have motion in the plane. Right? Before we just had motion on the line, now we have motion in the plane. Okay, so we have 3 pictures. We have the mu less than 0 picture. When mu is less than 0, what happens? There's the flow on, we know how the flow on x works. It's always to the left, because x dot is negative everywhere. Right? Because mu minus x squared, mu is negative, x squared is minus x squared is negative, negative. And now the flow on y is just down and swept along in x to the left. So on this line, when x is 0, it's straight down and straight up. Right? No, excuse me. No. That's not true. I'm lying to you. Right? It's just this way. Right? So no matter where you start, you just get swept to the left in x, and you go toward the x-axis in y. So that's all there is. Pretty boring picture. All right. Excuse me. I am having. Yes, right. Okay, fine. Right, because there were no solutions there, and now when, let's do mu equals greater than 0 first. When mu is greater than 0, we said there are 2 solutions in x, here and here, right? And the motion is that these are, right, x dot, when x is very large, x dot is negative, so the flow is this way. And when x is near 0, the flow is positive, so it's that way. There's an unstable fixed point. Right. Oh, we have, yes. This is not right. The flow is this way, and the flow is that way. Maybe. Okay. Right? Because we had a stable fixed point and an unstable fixed point. Right? Because when you have the birth here, one branch has to be stable and one has to be unstable. That's the way life is. Right? And so now we have to put in the flow in y. So now, if you're here, x dot is negative, is 0, and so the flow is straight down. Or straight up. Here also, the flow is straight down or straight up. At x equals, okay. And what happens in between? in between, so if I start here, somewhere there, I go down in y, and I get swept here, so I go into the stable fixed point. If I start here, it's just the mirror image, and I go into the stable fixed point. I go here, I go into the stable fixed point. If I start here, I go into the stable fixed point. So all in this area of the world, everything leads to the stable fixed point. In this part of the world, what happens is if I start here, I go that way. If I start here, I go that way. And I get swept to minus infinity. Y equals 0, x equals minus infinity. All right? Notice that this now is what we call a stable, this point now is a stable node. The x, when we were just talking about the x things, right, it was just a stable fixed point. Now we call it a stable node because it's stable in both directions. When we look at the two eigenvalues, both eigenvalues are negative, and so we approach this no matter what direction we're coming from, we go to the stable node when we're close to it. This thing now is what? That's a saddle. Okay. And now, what happens when we make mu smaller? When we make mu smaller, okay, let's put in the origin here, that's the origin, halfway between, right? When we make mu smaller, this point moves in this direction, this point moves in that direction, but the picture is the same picture, just rescale, right? I make mu smaller yet, right? And, you know, it's like that, so these two walls are closing in on the y-axis. So when mu equals 0, right, what we have, the only point of interest is we have the point at 0, and there now the flow along 0, along the y-axis is to here because x dot is 0 because mu is 0, and now the flow for x negative is negative, and the flow for x positive is also negative. So what happens is if you start here, you flow here. If you start here, you go off to infinity. And this was our half-stable fixed point in one dimension. And now, so this line, the y-axis, is a separatrix, right? Because anything that starts to the left of the y-axis goes off to minus infinity. Anything to the right of the y-axis goes to the stable fix, goes to the origin. Here, this is also was a separatrix. The y-axis here because no, excuse me. It's this. The separatrix is here, right? Because anything that starts to the right of x equals minus square root of mu goes to the stable fixed point from the left to right, and anything to the left of it goes off to minus infinity. So here we have this. This is why is this a separatrix? Because the separatrix, remember, always goes through the saddle. That's the nature of the saddle. It has always a separatrix going through it. And okay, and so this is that we have now understood why we gave this strange name to our bifurcation. Why is it a saddle node bifurcation? Because as we start with mu positive and take it smaller and smaller, what do we have? The saddle node collide and go poof. And then when mu is negative, there's nothing, right? Or run it backwards. You know, a saddle and a node, which is like a positron and an electron, are born at the moment of bifurcation. Right? Okay, so that is that story. So it's the same story, except that now we get to draw two-dimensional pictures. It's much, much better, right? And now the story is the same for everything. For the other ones that we did, right? We did the transcritical. Let's see. Okay, we had our transcritical, remember? Which was, right? X dot equals mu x minus x squared, y, and then we can promote this with to 2 dimensions with trivial y dynamics. The y dot is minus y, and then you can draw the flow diagrams, and we'll leave that as an exercise to the reader. And there's also, we had our supercritical.
Is it works in the homework?
What?
Exercise for the reader.
If I was in the Targelet, I would surely do it. So we had the supercritical pitchfork. Remember, there are famous, right? This one was the picture of, we had two fixed points crossing each other. That was the transcritical. This was the picture of our famous pitchfork, which is, we had, this is 1 to 3. This is 2 to 2. This was 1 to 3. 1, right? And the, which had this x dot equals yx minus x cubed instead of x squared, because now it has the symmetry of x goes to minus x. And then we had the subcritical pitchfork, and that was x dot equals mu x plus x cubed, so that it was, there's no stable solution. And what we see is, we had this picture here, is that here it was unstable, and then it goes like that, and like that, and that was our, then this part of the picture is the backward or supercritical bifurcation, like that, where this is stable, this is unstable, and then these two are also unstable. So this is a stable goes to 2 stables and an unstable, and this is a stable, it's run backwards. The unstable and 2 stables, the stable and 2 unstables go into a unstable. All right. So let us do, as an example, we'll do the supercritical. So again, we're going to add y dot equals minus y to the story, just to get ourselves some dynamics in the other dimension, and get ourselves yet another touche. The person who invented these things committed a crime against humanity. Okay, so now, what do we have out here? So we're going to do our supercritical here. And again, we have our 3 pictures. We have y less than 0, we have mu less than 0, we have mu equal to 0, and we have mu greater than 0. Okay. Okay. So what happens for mu less than 0? Well, the x dynamics, remember, so we have this story. There's one fixed point, and it's at 0. So here's our fixed point at 0. And now, so the dynamics this way is this way, and this is a stable fixed point, so everything goes to it. And therefore, and this goes up. And now we just connect the dots. We go in like that, we go in like that, we go in like that, we go in like that. And that's our beautiful, that's before the transition. Here we have 3 fixed points, an unstable fixed point at the origin. We have one at plus and one at minus. And so this flow is this way and that way, and this flow is this way, and this flow is this way, and this flow is down and up. And we have here the lines also are this way, and this way, and this way, and this way. Okay, and now we just connect the dots, or connect the arrows, right? You start here, you go into the fixed point. Start here, you go into the fixed point. Start here, you go here. 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 And start here, you go here. So the basin of attraction of this stable fixed point is everything to the right of the origin, to the right of the y-axis. The basin of attraction of this fixed point is everything to the left of the y-axis. This is a saddle, right? Because it's stable in this direction and unstable in this, so that's a saddle. And now this, and two stable nodes. All right, and now what happens when we may take mu smaller and smaller? Again, the walls close in, right? And at mu equals 0, the gap disappears. And we have basically we have the fixed point here, and in fact, the flow is like this. And it's really not any different than that, except that it is very slow going in, because x dot is like x cubed, so it's very small. So basically, it's just you take this picture, you collapse it, and so the only thing you have left is this part of the picture, and this part of the picture, and the middle disappears. All right, so that's your supercritical bifurcation, and that is that. Okay. And so let's do an example of a supercritical bifurcation, just to so I was supposed to do an example of a saddle node. So first let's do an example of a saddle node, right? We have the following example: plus y dot equals x squared over 1 plus x squared minus by. So it's now slightly non-trivial just to see what's going on, right? Because it's not trivial dynamics in y anymore. So we have to first find the fixed points, right? So the fixed points is y equals ax to satisfy the first equation, right? And then we plug that into here, and we get that x squared over 1 plus x squared equals by, which is abx. So we can get rid of one of the x's, and we have that ab times 1 plus x squared equals x, and you can solve for x if you want. And what you find out when you solve for x, so x is equal to 1 plus or minus the square root of 1 minus 4a squared b squared over 2ab. Right? And now you notice that there is, when there are two cases, when 1 minus 4a squared b squared is positive, then there are two solutions up here, plus the solution x equals 0, because we divided by x here. So there's always a solution x equals 0, y equals 0. And then there's the solutions y equals ax and x equals that. If a, in other words, if a, b is less than a half. So if AB is less than a half, there are three solutions. This one, which always, this one, and then these two. And if AB is greater than a half, then these solutions are gone. So here, so this solution is just always there. And here we have, for AB greater than a half, we have these two solutions are not there. And when AB is less than half, we have those two solutions. So this is a saddle node bifurcation. And to see what's going on, you have to look at the, first you have to look at the J of this solution. J is in general, because we have this, J, remember, is the matrix of partials. It's dx dot dx, which is minus a, dx dot dy, which is 1, dy dot dx, which is 2x over 1 plus x squared squared, and minus b. Right? So therefore, J trace J is negative. Right? And we have that determinant J is AB minus 2x over 1 plus x squared squared. All right, so now when x equals 0 for the one at the, so we have this fixed point at the origin, and now that has determinant equal to is positive and the trace is negative, so this is a stable node. And now we have two other fixed points. And they are given by these. And now, if you go through, you can see that when A, for example, so one of them has x less than, so we can write this as we can write the determinant in the following way, because we have that x squared over a, that AB x, yes, AB x over, yes, x, so we have AB, yes, AB x equals AB 1 plus x squared, so the determinant J therefore is AB times 1 plus x squared. No, we're going to write this, that's what we're going to write this as 1 minus, and now x over 1 plus x squared is AB, so we have that, we have a 2, and we have a 1 plus x squared down here. So the determinant changes sign depending on whether x squared is less than or greater than 1. Because when x squared equals 1, then the determinant vanishes. So it turns out that for the middle one, for the one with the minus sign, right? So we have the for the x equals minus 1, the 1 minus the square root over 2ab. X is positive and less than 1, and for x equals 1 plus the square root over 2ab, you can show that that is greater than 1, because the midpoint of the 2 is 1 over 2ab, and ab is less than a half, so the midpoint is actually greater than 1, and therefore the we have this one at x, here's 1, x greater than 1, and y equals ax, so therefore it's up here, and that is a stable node. And we have one that's here, that's slightly, well, it's bigger than, slightly bigger than 1, so it's like here. And the other one is sort of like down here, and that's an unstable. This is a saddle. Right, so this is a stable node. And this is a saddle, and as you take AB toward a half, these two come together and blow up. So that's how this, and this just sits here and does nothing. And this is the saddle node being born as AB goes through a half. All right. So yeah, you could draw the flows, but it's let's see. We have a whatchamacallit going through. Presumably, we have something like this, and stuff like this goes to here, and stuff like this. This stuff goes here. This goes in this direction. It's a good question. Let's see, because this is the unstable direction, and this is the stable direction. So I guess so. Therefore, this is trace is. What was the trace was a minus AB. The trace was negative. Did I do something? Okay, when these things don't work out. This looks like it goes down here. Everything would make sense if that was something is wrong with the picture. What is wrong with the picture? I guess I have, let's see, the determinant, when x is bigger than 1, then the determinant is positive. Yeah. And so that's stable. And the other one.
Should they fixed points on the same straight line?
The trace is negative. Right. No, the trace is always negative because that's simple. That's minus a minus b. The question is the determinant. If x is the larger one, then the determinant. Yeah, this is bigger than 1. This is a smaller number. AB is the determinant is positive, which means that they're both both eigenvalues are negative. Whereas here, one's negative and one's positive. I just don't get the arrows to work out for me the way they're supposed to. Because I didn't write it down. I didn't do it beforehand. Because you assume it's trivial. And, all right, it's an exercise, another exercise so that we can get this right.
That should all of this falling on the same straight line?
What?
Like y equals to ax?
This y equals ax, yeah. So I mean, this whatever x this is, y is positive on both of them, right?
Right. They
Right.
have to be in the same
Yeah, this is my problem. Yes.
Yes.
This is this. Here's 1, and this is this.
Correct.
So this is the saddle node. This is the saddle. And this is the node. And now let's see if we can get this. This is the unstable direction. This that way. And now it flows this way. It flows to here.
Actually, the origin is on the same line. The 3 fixed points are the same on the same straight line.
They're all on the same straight line. Yes, because y equals ax. Right. So we have this and that. Okay. So now this flow is this way. This flow is that way toward the fixed point. Very good. Then we have a direction this way, going out that way, and out this way, and then everything here goes to here, and everything here goes to the fixed point. So, and this is our separatrix. Thank you. Okay. Somehow my brain is not engaged today. Okay. So that is our supercritical bifurcation. That's our saddle node bifurcation. Now, do one example, hopefully a little better, of this transfer of the supercritical pitchfork. The example we have of the supercritical pitchfork is supercritical pitchfork. Here we go. Yes. X dot equals mu x plus x x plus sine x, and y dot equals x minus y. All right, and the fixed point therefore has to have x equals y, and then we look at this equation, and their x dot equation says that mu x plus sine x equals 0, and so things happen in the vicinity of x equals 0, as we'll see with near the, and because there's a symmetry that if x goes to minus x, y goes to minus y is a symmetry, so you know that things are happening close to the origin, because that's the only place that the two could be born. When x is small, we can approximate this as mu x plus x minus x cubed over 6, because that's the approximation of sine equals 0. And this is that mu plus 2 times x equals x cubed over 6, and the solutions are x equals 0, and x squared equals the square root of 6 mu plus 2, x equals the square root of 6 mu plus 2, and mu critical is minus 2. So that's the pitchfork that happens, and when mu equals minus 2, when mu is greater than minus 2, then we have our three solutions. When mu is less than mu critical, then we only have the x equals 0 solution, and so that is the way that works. Okay, and then y is and x equals y. So all this, everything is happening on this line, and so we have this is born here and this is born here, and they come together. And, all right, and so then this is unstable on this is unstable, that's stable. And so this is stable in this direction, stable in that direction, and goes this way, and so the flow is from here. So anything. So we have this goes here. This goes to here. This goes to here. This goes to here. And so depending on what side of the separatrix are, you go to one of these fixed points. All right. So that is our story of. And then you can do the same thing for the subcritical. Again, for the subcritical, you have to put in, you can't just look in, because you can't find the stable solution in the vicinity of the bifurcation point, because it flows away from here, and you have to actually know the full nonlinear function in order to find the fixed points. Okay, so all that is trivial generalization of what we did, except for drawing the stupid pictures, of what we did in one dimension. There's one new thing. So the new bifurcation is our friend Hopf's bifurcation. And a Hopf bifurcation is what is in our diagram when we drew our trace determinant. What was it? That was but which way was it? It was trace determinant, right? And we had this picture, and what we had here is we had stable. Here we had stable spirals, and here we had unstable spirals. And as you go through that line, well, or you actually, well, let's put it the other way. When you go through, when you here, then the center is the where the fixed point is stable, and that's where you go to. But as you cross this line, that point becomes unstable, and instead of spiraling into the fixed point, you spiral away from the fixed point, and then, if you're lucky, or So a lot of times what happens is you get a periodic solution, and so you get a limit cycle. And the birth of the limit cycle from a stable spiral turning into a limit cycle is the hot bifurcation. It's exactly what happens when
you need to switch the determinant in the tracing.
Yeah, hold it out.
Because you need, if they're in different if the eigenvalues are different signs. So
here
the determinant is negative.
Here the determinant is positive.
So
right. Here the determinant is positive.
If the determinant is negative.
Right. This is the determinant in that trace. Yeah. Right. All right. So how does this work? So let's write down an example just to see how things work out. So there's the trivial example is r dot equals mu r minus r cubed, and theta dot equals omega plus br squared. All right, and since this is r is decoupled from theta, we can just think about the r dynamics for the moment, and we see that in the r dynamics, there is, when mu is negative, then r equals 0 is the only solution. And when mu is greater than 0, then r equals 0 is unstable, and the solution is r equals plus square root of mu. And not plus minus, because r is a radius, right? So now, to see this in terms of normal bifurcation theory, let's write things in terms of x and y. If we write down that x equals r cosine theta and y equals r sine theta, as it's traditional, then x dot equals r dot cosine theta, right, plus minus r sine theta, theta dot, right? Now r dot is mu r minus r cubed, and cosine theta is x over r. And now we have r sine theta is y, and theta dot is omega plus br squared. So that's bx squared plus y squared. Right? So now the r goes away, and we have the linear pieces are mu x minus omega y plus nonlinear terms. Right? Because we have here mu r times x of r is mu x, we have minus omega y, and then this is nonlinear. So we have x dot is that. Now y dot is r dot sine theta plus r cosine theta theta dot, which is r dot is again, so this is y times mu minus r squared, and this is x times theta dot times omega plus br squared, and now again the linear pieces are mu y plus x dot omega. All right, so now we can write down the behavior near the fixed point at 0, right? Which was the stable is the stable solution for mu less than 0, and we should find that out because the Jacobian is mu minus omega and mu, which is mu squared plus omega squared. And the trace, so the determinant is this, and the trace is 2 mu. So when mu is greater than 0, right, so the two eigenvalues are in fact mu plus and minus I omega, right? That gives us a trace of 2 mu and a determinant of mu squared plus omega squared. So lambda plus minus is mu plus or minus I omega, and if mu is negative, then it's stable. and if mu is positive, it's unstable. But in all cases, it's a spiral because it's got an I omega there. So it's a stable spiral for mu less than 0, and then the origin is a stable fixed point, and when mu is positive, it's an unstable spiral. And now, but then we know what happens, because we know that the solution is that we have a circle at radius square root of mu, and it just keeps going around with a theta dot, which is omega plus b mu. Right? So that's all well and good.
Why do you need to go to the xy plane?
Because to do, in principle, you don't, but then.
And you are focusing on the problem near the origin.
Yeah,
and so
R is a singular coordinate system. The problem is it's a singular coordinate system at the origin. So that's.
But you are ignoring the non-linear terms.
Right, because it's near the origin. Everything mu is small and we're near the origin.
So you can ignore it from the beginning. That will be very trivial problem.
No. You need the R cubed to restabilize it, right? I mean, yes. To look at the stability, then you can throw away the nonlinear terms, right? But if you want to actually figure out what happens later, right? Whether this is because this is an example of a supercritical hot bifurcation, because the limit cycle that's created has a radius which is the square root of the distance to the bifurcation.
Yeah, I agree. But your analysis there is near.
Right. The linear analysis. The looking at characterizing the fixed point and its stability. I don't need the nonlinear terms. True.
If mu equals 0, then the fixed point is still stable.
It's a center, right? And then we said, when we talked about this a month ago, we said that centers can turn into unstable or stable spirals depending on the nonlinear terms.
Okay.
So the only way to see what happens is, and then so you see that when mu equals 0, it's stable, but it's not. It's non-linearly stable because r dot is minus r cubed.
Yes. Okay.
And so right.
All of those nice things, does they have connection to a real physical system? Can you give me an example? We saw pendulum, for example, but
no. So we'll get in. We'll get there.
I'm feeling that.
Okay, we're getting there. Just give me a minute. All right. So, in fact, I think that is the next. If I can make sense of my notes, let's just make sure that I don't skip anything. Okay. Now. Let us turn to a example. You wanted an example. Here's your example of something that's a little more physical. Okay. You remember our favorite problem, namely the van der Pol oscillator.
Yes.
Right?
Yeah, but van der Pol oscillator, we
didn't mention, right? Because when we looked at it, we looked at a parameter which was beyond the bifurcation, where there was a limit cycle. But we can talk about it in general, and that's what we're going to do now. So
but what does the the differential equation present physically?
It's a kind. What you could build one. I mean,
How
do you know? I mean,
but
you're talking to the wrong person if you want to know how to build it. But
no. I'm not asking how to build a system that.
But
its differential equation will be under.
Well, obviously,
where
the point
you will find it.
Yeah, that's I'm sure there are examples of, if you go to Wikipedia and look up van der Pol oscillator, I'm sure they'll tell you why Mr. Van der Pol invented the equations. It wasn't just as a mathematical.
It's something with climate physics, but I'm not sure.
No,
No, you don't.
No, I don't think so.
Okay.
It's a circuit. You know, you can build it as a circuit with adjustable gain. I mean, right? It's an oscillatory RC circuit with a nonlinear element in it.
But that not giving me much intuition. I want to get.
Okay.
Yeah,
Well,
I understand this.
Okay. Well,
Yeah.
I mean, all right. And this is so before. Okay. So now what we're going to write is the following: plus mu x squared. Right. Now before we wrote x squared minus 1. Right? Now we're going to write x squared minus epsilon times x dot plus x equals 0. Right? So this is our linear oscillator, and this is our nonlinear oscillator. When x is big, it has it decays. It's got it's got loss, and when x is small, it has gain. The amount of gain depends on, and that there are lasers that that work that way. When the amplitude is big, you get. That's why you have a lasing instability. Mm-hmm. I mean, I'm the wrong person to talk about this, but there's a lasing instability, right? Yeah. And then at some point it's self-saturating, which is this kind of. So if you write down the equation for the electric field amplitude, it'll be something like this. Mm-hmm. Not exactly the same, but something in that spirit, because it self-saturates. Otherwise, the laser would have blown up, right? Mm-hmm. So for small amplitudes, you get gain, and then at some point you deplete the inversion layer or whatever.
Will we talk in the general question? Will we talk in the course about partial differential equations?
No.
No.
I was actually hoping to. My original plan was to talk about them, and then they cut 4 weeks out of the semester, and so maybe by the last week we'll get there, but that was the hope. But
there's somewhere that I can see those missing lectures.
No, because it's not in the book. They're in this book, and so I hadn't written up the lectures yet because it was summertime. Okay. Anyway, the point is, before we had 1 here, and then we saw that you had a limit cycle, right? Now we're going to see how the limit cycle was born. Because we have this new parameter epsilon instead, and as we dial epsilon, when epsilon is negative, right? When epsilon is negative, then both these terms are positive, and therefore you only have loss and no gain. So of course you get no sustained oscillations. When epsilon is positive, right? Then there's a region of small enough x for which you have gain, and so therefore you have some degree of you pump energy into the system, and you get a finite amplitude oscillation. And the amplitude of the oscillation, it should not surprise you, goes like the square root of epsilon, as we will see in just a minute. All right? So what did we do before? Let's do the same thing we did before, because it works so well. Right? What did we say? We said we'd look at the energy. And the energy is 1/2 x dot squared plus x squared. That's the definition, if you will. All right, and then we said, okay, E dot, okay. So E dot is x dot times x double dot plus x like that, right? Because there's a half here, and then, all right. And x dot plus x, so this is x dot, remember, times mu minus mu times x squared minus epsilon times x dot, so that becomes x dot squared. Right? And we said, okay, before we were looking at, right, so we were when we did the analysis originally, we said mu was very small, and therefore the change in things in a single cycle is very small. We're going to continue along those lines for the moment. We'll generalize in a minute, the general mu, but let's go back to, we're still doing what we did before, right? So we said that mu is very small. So if mu is very small, then the change in the structure of the orbit over one cycle is infinitesimal, because the amount of energy you're losing is infinitesimal, so therefore the amplitude is going to just shrink by a tiny, tiny bit. And so we calculated the delta E over one cycle, and we said it was minus mu times the average of x squared x dot squared minus epsilon times the average of x squared x dot squared. And x, remember, was a slowly changing radius times cosine t. So therefore, the average of x dot squared was r squared times cosine squared t average. And the average of cosine squared is a half, so we got 1/2 r squared. And we have x squared times x dot squared average. Remember, that is cosine r to the 4th cosine squared sine squared, which was r to the 4th averaged, which is sine 2t squared average over 4, and therefore this was r to the 4th over 8. And so we have the delta E is equal to the average rate of is mu minus mu times r to the 4th over 8 minus epsilon r squared over 2, and therefore this was d dt, which is therefore r dot, and we got that r dot. We got this equation for r dot, which was r dot is minus mu r cubed over 8 minus now epsilon r over 2. Right? And therefore, now we see that what is r equilibrium, what is r of the limit cycle? R of the limit cycle is when r dot is 0, and therefore we get that r squared equals 4 epsilon. So r equals 2 times the square root of epsilon. Right? And in fact, when what we got before was epsilon was 1, and we had a radius of 2. And so in the small mu limit, r is 2 times the square root of epsilon, independent of mu. All right? Now, let's do it a little more general. All right? Because what we are now going to use is the fact that near threshold, when epsilon is small, r is of order the square root of epsilon. That's what we're going to use. All right? So we're going to write that x equals x naught, which is x naught is, we're going to write it as the square root of epsilon times a naught times cosine t. That's the unperturbed thing, right? Because here, so now the justification for saying this term is small is not that mu is small. It's because x is small and x dot is small. So therefore, if x is of order square root of epsilon, then this is epsilon to the 3/2. And this term is epsilon times epsilon to the 1/2 is epsilon to the 3/2. So this term is now small, because not because mu is small, but because epsilon is small. All right, so it's the same. It's going to look the same, but in fact, the thought process is, the justification is different. We're basing ourselves on the smallness of epsilon, not the smallness of mu, because we saw that this answer worked for all epsilon. That was positive, right? Now we're going to do it here. And what do we get? We get this plus x1, right? Some perturbation. And x dot, therefore, is the square root of epsilon minus a naught sine t plus y1. And yet another marker bites the dust. I think we're here. Okay. So now what we're going to do is we're going to plug this into this equation and see what happens. All right. So we have x1 double dot plus x1 plus x1. This is plus x1 dot. That's what it's right there. So we have x1 double dot plus x1 equals minus mu times, now we can use for this, we can use the fact that x here is x, replace x with x naught here, right? Because we're doing perturbation theory, and therefore this is a naught squared cosine squared t minus epsilon. This has an epsilon here, minus epsilon times x dot, which is a naught square root of epsilon minus sine t. Right? So this is x dot, x naught dot. This is x naught squared minus epsilon, and we have a minus mu here. Right? So this is our oscillator, and this is our driving term, right, which is small, and therefore what we get is that, okay, and now we're going to write that minus, we have minus mu epsilon to the 3/2 as a general factor. We have an a naught here, and now what do we have? We have a naught squared times cosine squared sine times sine. Let us rewrite that. Everybody knows, okay, so cosine squared times sine, right? And right is, okay, yes, cosine squared times sine is e to the plus minus e to the minus it, but who needs to write the it's? Right, over 4 times e to the plus, this is plus, squared, and now this is e to the minus over 2i. Right? So this is e to the plus 2 e to the 0, so we'll just write that, plus e to the minus 2 over, so this is 2 here, and then we get the 4, and this is e to the plus minus e to the minus over 2i. Okay, we get a term which is e to the plus 2 times e to the plus is e to the plus 3. And similarly, we have an e to the minus plus e to the minus minus e to the minus 3 over 4 times 2i. So this is just sine 3t over 4. All right, and then this term is we have 2e to the plus. Here, this gives us minus e to the plus. E to the minus, so that gives us plus 1 over 4 times 2i e to the plus minus e to the minus, and this is sine 3t over 4 plus sine t over 4. All right, that's that. If I did it right, hopefully I did it right. Let's just check myself. Yeah. Okay. Okay. Right. Okay, great. So now, what do we have? We have a naught squared times 1/4 sine t plus 3/4 sine 3t minus epsilon sine t. And now this becomes plus here, and we get that. All right. So now we have a linear oscillator driven at two frequencies, driven by a sine 3t signal, which is off resonance, and we have our sine t signal, which is on resonance. And we don't want resonance, and therefore it has to be the case that this thing has to cancel, the sine t here has to cancel that. So the condition to not be at resonance is that 1/4 a naught squared equals epsilon, or a naught equals the square root of 2 epsilon, which is what we found before. But this is only true now. This is independent. You see, it's again independent of mu, as it happens. And this is true. However, the justification for this is not small mu. This is for any mu, but for small epsilon.
The 2 goes out of the square root.
Yeah. I'm doing fancy math and I can't take a square root correctly. Okay. Okay. Very nice. So this is how you do things in general. And so basically any problem that involves a hot bifurcation is for small amplitudes, it's going to be a circular or elliptical orbit, depending on how you define y. You know, if you talk in terms of x and x dot as your coordinates, it's a circular orbit. Otherwise, if you have an x and a y, and the amplitude will be something times the square root of epsilon. And okay, so that is our van der Pol oscillator. Okay, and one more. I want to do one more example, which is actually comes. There's a. All right. Following system. It's x dot is minus x cubed minus y, and y dot, and in principle we're going to put here divided by epsilon for good measure, and y dot is equal to minus x plus by minus a. Okay? Now, where this comes from, this is a model of two reacting species, in fact. And if you look in the book, he has slightly different right-hand sides, but the geometry is the same geometry, and the math is a little easier here. So, but this models two chemical reacting systems. And as we'll see, sometimes, depending on parameters, you can get a hot bifurcation out of this thing. So in order to find the fixed point, let's draw the null lines. Right? The null clines are where this vanishes l'chud and this vanishes by itself. So if this vanishes, that says that y equals x cubed minus x cubed. And that looks like, oh, darn it, I don't want that. That's not what I want, so I screwed up. I need a, yes. I need a, x cubed, y, yes. So y equals plus x. Yes. Okay, so I get something like this. Right? That is, so y equals x cubed minus x. Minus x cubed minus x. Right. Yes.
You're supposed to have maximum, minimum.
Yeah, I want the. Right. So there's a minimum, right? The minimum is minus 3x squared equals 1. That's not good. What am I doing wrong here? I want.
Probably it's supposed to be plus x.
Yeah.
Yeah, plus x.
That, no.
Yeah.
Yeah. And now when you upload.
Right. That's the way to look. Right. Okay. Yeah. Okay. So we have that thing, and now this thing is y equals x plus a over b. Right, which is a line that looks like, which, depending on a and b, can intersect either here or can intersect somewhere here. And as we'll see, the story is completely different depending on where it intersects. So let's imagine it intersects here first. All right. So, right. So we get df, the Jacobian. Let's see if we can do this correctly today. Minus 3x squared plus 1, right? Minus 1, minus 1, minus a. B.
It's only B.
B plus B. All right, so this is b times 1 minus 3x squared plus 1.
Minus.
What?
Minus.
Minus 1 is the determinant. And so the other, and the trace is b plus 1 minus 3x squared. All right? So this is going to give me what I want. Let's see. B times 1 minus 3x squared. And so the trace yes. Yeah, that's why is this not working out for me? All right, I have to put in a parameter here. I put in a parameter there, then this becomes that, and therefore I can get multiply this is minus C. Right. Okay, so if 1 minus 3x squared is positive, right? Then and B is positive, then this is positive, and if C is small enough, then the determinant is positive, right? And now this is positive, and nah, that doesn't do me. That's not going to do it. That's not going to do it. Why is not going to do it? All right. Point of the exercise was, and I'm sorry, I thought I had this worked out.
Yeah, it's okay.
I just made an algebra mistake writing this up. So you have, when the intersection's here, you can arrange, if you arrange things correctly, you can get that this is can go through a hot bifurcation. And we're not getting that right now because it's always, trace is always positive. And so it's always
Oh, it's always positive.
Right. So we don't get a hot bifurcation, but there's some way to get this.
No, it's not always positive.
If because if you need the determinant to be positive to have a complex.
Yeah.
Right. We need the determinant positive, which means
determinant positive.
If this is negative, the only way that trace can be negative is either B is negative or this is negative.
But it depends also on C.
The determinant.
Yeah. So you.
But if this is if one of these two has to be negative for the trace to be negative, and that means this is negative. Oh, so C is negative.
Both
yeah, no,
yeah.
but, right.
Also,
but that's.
both of them could
but
be
in
negative.
my mind, In my mind, I know that the example I worked out is that this line goes with positive slope. I'm pretty sure, but I'll.
Yeah, but
So
it doesn't matter without
If it went like that, then for sure, then okay. So if it goes through like that, let's imagine it goes through like that.
Maybe also you can have both of them be negative, so the multiplication is positive.
You want both B and.
Yeah.
Right. Okay. Right. All right. So both of them, are negative. Then, but still, the point is, then the line goes. Then A,
yeah.
Then the A
that's
still
what
be.
you want. And then your.
Okay. Then C can be negative, so I can take B to be negative and C to be negative, and then everything
needs to be large. Yeah.
And then it works. Okay. And so in any case, you can adjust parameters that this is a hot bifurcation, and then so you get oscillations around that point.
Yeah.
Right? The other case is if you have the same thing, but you just move this, change A, you can now slide this thing. So this is exactly the same as before. And we have this. And now if you go here, you can now show that this thing is a stable fixed point. And now what's amusing about this is if you have a small perturbation around this, it's stable because it's a stable fixed point. So any small perturbation around this thing just goes back to the fixed point. But if you take a large perturbation, then in fact what happens is, that's my problem. That's my problem is that it had to go the other way. That's my sign. Right, it had to go the other way, like that. Right, it has to go this way. That's what it screwed up. Because now, if you take it over here, then in fact, the flow which was here, this is an unstable fixed point in the x motion, and so it flows this way. And then if epsilon is small, it's trapped on this line, goes up this line, until again it can't do that anymore, and it goes here, and then comes back, eventually comes back down to the fixed point. Now, so what happens here is, so this, you have a fixed point that for small perturbations is perfectly stable, but if you give it a big kick, it still comes back to the fixed point, but it takes, the time it takes to get back to the fixed point jumps discontinuously as I go through this line, and from a small time back, in order one time, it can take a very long time to get back to the fixed point. So this kind of system is called an excitable system, which is the point I wanted to make. This is called an excitable system because it's stable, but if you excite it, then it takes a long trip around until it finally gets back. And now this, in fact, is a model of chemical reactions. It's also a model of what happens in how your nerves propagate signals. That the concentrations of you have electrolytes in your cell, in your nerve cells that are passing, that create potentials and stuff like that. And if you give it a small little perturbation, nothing happens because you don't want the thing to just, for every time something happens, you go, the nerve starts firing. But if you give it a large enough, finite size perturbation, then it fires and then comes back and relaxes again. So this, and then this is, there's a something, the model, there's a model called the Hodgkin-Huxley model, which I should have just looked up what the equations for that were. The Hodgkin-Huxley model, something like that. Two guys who wrote down, who were actually biologists studying nerve propagation, they wrote down this model, and this model shows you how a nerve fires. And it's also explains, it uses, this model like this is used as a model of the heart dynamics, why a heart beats, because it gets a signal from there's something in your heart that introduces a signal, and then the muscle contracts. And so this is a kind of interesting two-dimensional nonlinear dynamics, which is neither a limit cycle nor anything else. It's just a relaxation, but a non-trivial relaxation back to the fixed point. And with that, we are done our story of two-dimensional dynamics. And in fact, as I'll claim next week, in fact, there's nothing new. Okay, then there's the big mistake of Landau. All right, one of the gods of physics, there are a few gods, Einstein. There's Newton at the top of the pantheon, and then sitting at his knee is Einstein. You could argue which one is which, right? And then below that, then there are a bunch of guys, but one of them was Lev Landau, right? Died around 1968 or something like that.
Same Landau
from Landau and Lifshitz, yes. He was the god of Soviet physics. He was also the father of the Soviet atom bomb. Among other things, he also invented quasi-particles. He won a Nobel Prize. He said that in the logarithmic scale of intelligence, Newton was a 0, Einstein was a 1, and he was a 1.5. So he was a very modest fellow. So Landau wrote an article at some point, and he claimed basically that there's nothing new that happens in higher dimensions. That all that can happen, because what happens is you have a larger dimension Jacobian, and if there are multiple unstable modes, then nobody cares, because you'll never get there. So it plays no role in the dynamics. That is anything. The only things that are very interesting are stable nodes and saddles, i.e. things with n-1 stable directions and 1 unstable direction. Because that determines the dynamics, because you get the saddle node bifurcations, etc., etc. Anything with higher things is irrelevant. So you can always project the dynamics onto the two most stable modes, one of which is stable, and the one of which is is stable, and the other one might go unstable, and that's all there is in life. And that's what he said. So there's nothing new, he said, in higher dimensional dynamics. And he was wrong. It's his most famous mistake. And the fact of chaos, which came along in the 1960s, in the late 60s, right after he died, proved that he was wrong, that there's something interesting that happens actually in 3 dimensions. 3 dimensions is a critical dimension for a new kind of dynamics, which is not anything that we've seen before. It's not a limit cycle. Has nothing to do with fixed points. It's something new and different, and that's the topic of the next few lectures.
It's the Lorentz equations, right?
Yeah, right, exactly, which are 3-dimensional equations. Right, so that's what we're going to talk about next. All right, have a good evening. What? No, no, I don't think so. I don't think so. Don't think so. He was obviously Jewish. That there's no question about. But as far as I know, not. But it's an interesting question. No, he was. First of all, Russian physicists were not allowed to have political positions. So yes, when the Russians turned against Israel in the 1950s, he could no longer afford to be a friend of Israel, even if he was a friend of Israel. Right? Because if while Stalin was living, and even for the next decade afterwards, if you expressed opinions which were against the party line, then they knew what to do with you. And in fact, he almost was sent to the Gulag, even without that.
Oh, why?
Just for the prison camps of.
Oh yeah. Okay.
But they needed him to do work on the bomb, and so they. Yeah, no, and what's the most amazing thing, which I discovered only about 10 years ago, is he was awarded the Lenin Prize or something like that. And the point for his work on the bomb, and a couple other people, Kurchatev, Tav, or something like that, and it came with not only a medal, it came with money. Because for all the communist propaganda about socialism and everything else, they knew that if you wanted results, you had to pay people money to get it. So you had to reward people, right? Even though the money wasn't good for anything, because what could you buy in Russia with money? So you could buy a dacha, I guess, if you also were, but you needed money by it. But that was the point was it wasn't just enough to give him a pat on the back. They actually had to give him money. So that sort of there's a lesson there to be learned.
You have one. Tutorial number 6. Okay, this tutorial we are going to talk about limit cycle. Okay? Limit cycle. What does it mean? That means that instead of a fixed point that we are going to it and stay there, we will going to finish at some it not have to be in shape of cycle, but some closed loop. Okay?
not good.
Okay.
Can I change?
This one?
Okay.
In the screen you can just change the resolution. in YouTube.
Okay.
And
To 180, yeah?
yes.
Okay,
Yeah.
yes, I know. Okay.
Okay. And as in a fixed point, we have a stable limit cycle. Okay, that from the inside will go here, and from the outside this. Okay, this is stable. We can have an unstable, right, that starts with close to the cycle and go out, and inside it will do
נראה לי כולם פה
this,
דוברים עברית.
but the course is in English. And
זה מוקלט?
yes,
אוקיי.
and we can have also the option that from the one of the side it will go to the line, and from the other side it will go farther from the line, and then it will be a half stable. Okay, so we have stable, unstable, and I have not another color,
And
but
there is a cycle of fixed point, right? There is a closed loop of fixed point because it's supposed to be continuous. Think about that.
Yes
if
and
you're
no,
getting
because
closer and closer,
but it can go on this cycle. Like maybe the particle will be
I'm talking about the direction.
Yes.
I'm talking about the direction.
What
The
do you mean?
direction, if you will look about, if you will define anti-clockwise to be 1 and clockwise
To be zero
to
or
be
minus 1?
0 or something.
Okay.
I don't know, it's supposed to be steady between or something like that.
No, imagine that.
If you're getting closer and closer with the radius.
But you don't have to.
Okay.
Maybe we are in more than one dimension. So
Yeah, that it doesn't.
look at a pendulum, right, in 3 dimensions.
Mhm.
So it will do something like this. So it's circle.
Okay. But there is conservation in the.
It is not
Arc.
some point in the space that it go to there and stay there. It is some trajectory that it will
Okay,
stay
yeah.
in this trajectory.
Yeah. Okay.
Okay. Okay. Rolling out those orbits. How can we know that there won't be a closed loop? First option is gradient systems. Okay, in system like this, we suppose that we have some function v, okay, of x vector, such that x dot is minus del of the divergence of it. Okay, from now all the x will be x vector. Okay, until I will say something else, but for now. Okay, so if we have some function v that this is the gradient, there are no closed orbits. Okay, proof. If we will do the integral over
Use the Stokes law, Gauss law.
Gauss law will be in some
So it's Stokes law.
next. No, I don't think I will use it.
Okay.
I mean, okay, that's it.
Hey, okay.
From one hand, delta v is 0. right? Because we are doing a circle and we are coming back to the same point. Okay? From the other hand, delta v is the integral from 0 to t of dv dt dt. And this is actually, you can write it as del v dot x dot dt. Okay? Right. And this thing is actually why? Because we did dv by dt, dv dx, dx dt. Okay, dv dx del v.
Don't you need to add the v is independent of time, okay?
Yes.
Okay.
So this is actually the norm of x dot, right? Squared. And this is always lower than 0. Equal 0 and lower, so there is no. Okay, there are no closed loop. Okay, second way. A Lyapunov function. What is the Lyapunov function? We have the system x dot equal f of x with fixed point x star. Again, x is vector. Okay, all of them. Okay, suppose that we can find a Lyapunov function. Okay, what it means? That there is some function vx. Okay, that exists first. Vx is bigger than 0 for all x that is not the critical point, and at the critical point is 0. And second, v dot of x is lower than 0 for all x is not the critical. Okay? This proof is a bit large, but the main idea is, imagine that we have the potential Vx. Okay, here we have the x star, and just during the time they will go down. Okay, this is the main idea of this option. And third way is
אפשר שאלה?
yes.
הדלטה V הוא כאילו אמור להיות שלילי.
Where?
שאחר כך שהוא 0.
The V is the like the potential, okay, and some point, and the delta V, that means that is V on T1 minus V on T2, but we are coming back to the same point, so they are equal. Okay. And Dulux. Yes, Dulux. Carry on. Okay, let x dot equal f of x. If there is gx such that
רגע, אז בשביל מה עשיתי את האינטגרל, אם באמת עכשיו את ההסבר הזה עם המחזוריות? בשביל מה עשיתי את ה...
to prove that there are no closed loops.
There are no what?
Closed loops in the area. We said that, okay, if there is a closed loop, this is what will happen, but it cannot happen.
הבנתי.
רגע, בשתיים, how does V, איך מוגדר V? כאילו מינוס אותו דבר?
You just need to find a function. Okay, it is not.
Gradient?
No, it's not have to be a gradient.
אבל יש לי F ויש לי את V, איך הם קשורות?
I'm sorry, wait.
F is like minus gradient of V.
open the book because I'm not exactly sure. I think it should be, but just a minute. Okay, the Wi-Fi is a bit slow, so I'll check it in at the end. I think that yes, it is a gradient, but I'm not exactly sure. So at the end of the tutorial, I will return to the book.
What is the problem?
The connection between F and B. I think it is a gradient, but let's check again. Okay, so the last criteria. No, wait a minute. No. Wait. I think it's like this. There, I don't. Okay. We will see that in the exercise, but I think it's like this. There is not have to be a connection, but it is related to the. When you build Vx, so you have some behavior of x dot and y dot, and I think this is how it affects between the two. This is what happened here. So maybe we'll see. I think in the when we solve some exercise. Okay, so relax. If we can find some G, don't related. Okay, if we can find some G such that the divergence of G x dot is not change its sign, okay, in some area AR inside the whole space. Okay, so inside R there are no closed loops. Okay, how it works. So here we will use a green theorem. Okay, so for that, this is R, okay, in the area, and there is some closed loop C. Okay, if you are looking, if you are looking on the integral, this one. We can write it also like this, while we have this is n, right, in this direction, and this is, I'm sorry, not say that, x dot, right?
That is the divergence, right?
Yes. Okay, but we said that this is not change its sign in all this area, so this have to be not equal to 0, right? Different from 0, but x dot n, this is actually 0. Okay, so again, it cannot happen.
The condition for additioning. The condition.
For this gradient, the divergence of g dot x. Okay. Establish the of closed orbits. How can we know that there are closed loops? So again, we have some methods. First, Poincaré Bendixson. If we have x dot equal fx, and again r some closed area in the space, where am I? Okay, if there is some trajectory, if we have r, and there is some trajectory that will stay inside r for all the time, okay, it's not really matter what it is shape, but it's always from the beginning to the end inside R. That means that there is a closed loop inside this area. Okay? Even this trajectory is not a closed loop, there is here. Okay, first way. Second way is Lינארית system.
Do you consider a stable point a closed loop?
Inside a closed loop, there is a stable.
No, but do you consider if I find such R and yada yada yada, and in this R we have we could have a stable point with no closed loops. So
yes.
So a stable point is a special case of closed loop. כאילו היא לא אומר לנו, אומר לנו שיש או נקודה יציבה או גבולה. יכול למשל ספירלה.
This sentence?
כן.
No.
אבל אם יש לנו ספירלה, אז לכל נקודה יש כאילו תחום R של כל נקודה בתוכו, נשארת בתוכו.
No, but from, if you go, like, for anything.
For any starting position? For any initial position? You stay inside R or
No.
outside R? Then R itself.
Okay, I got you. Wait. If you have it is yes and no. Like you can also say that. Well, actually, yes. It's also to say that centers are also, but it's not really interesting. So yes, but we care for now about the more interesting. Okay, second way, Lינארית system. Okay, the Lינארית equation is x dot plus fx x dot plus gx equal 0. There will be a stable a closed orbit if 1, let's do it a g is an odd function. Second, g is positive. Okay, for third, f is an even function, and then we define the odd function f as the previous of f, of small f, a, and we want first that f has one positive 0. Okay, it's x equal a. Second, f.
זה אמור לתאר מערכת reversible? כי גם בזה של reversible יש משהו עם פונקציה זוגית ופונקציה אי-זוגית.
But in the reversible we define it like this.
אז אם נגיד אני מגדיר y שווה x דוט או משהו.
Let's try. If we're doing
מה המערכת הזאת מייצגת?
dot, so it will be minus gx minus fxy. If g, I don't think so. Because if g is odd, so this will flip you off. It will be gx and minus. Yes, I don't think.
Okay.
Or yes, let's see. I said xy. No, we change. Yes, no. It will flip here. The minus. So no.
The stance of it?
What? The odd and even?
Okay.
No, it is how it's built. How Lינארית
כאילו הדמיון הזה שיש לי בין זה לבין איך שה-reversible מערכת
Yes, I think.
ומה המערכת הזאת מייצגת פיזיקלית? כאילו, איזה סוג של מערכת?
We'll see. We'll see examples. Okay, so second, f is negative at the area between 0 and the 0 point of f. Third, f is positive and non-decreasing for x lower than a, and for fx going to infinity as x going to infinity. Okay, so these are the methods. Exercise. Question about the definition? Okay, exercise 1. Given the system x dot is 3x squared minus 1 minus e to the 2y, and y dot minus 2x e to y. Find the potential, find the potential function v such that x dot is minus this. Okay, solution. How will we do that? Let's first denote the orbit, okay, at a fixed point, okay. Where am I? Okay, and we want to show the Lyapunov conditions. Okay. I'm sorry. It is not this. Suppose that. Okay. Not. Is it really? Yes. It's not the safe point. Yes. Okay. So we want to find the potential. Suppose that there is a potential like this. Okay. So we can write minus the v, the x is x dot, and minus the v, the y is y dot. Right? Let's do the integrals. So we get minus v is x third minus x1 plus e to y plus the function of y. And for the second one, minus v equal to minus x e to the 2y plus h of x. Right, so in total, v of x and y is minus x third plus x 1 plus e to the 2y. Right, so we find potential.
Just
Okay. Next, for the system x dot is minus x plus 2y third minus 2y 4, and y dot is minus x minus y plus xy. Show that there are no periodic solutions. Means closed orbits. Okay, it is periodic. Okay, choose A and N such that V is from this shape and is a function. Parasite? No. Yes.
Assume there is no dependency on parameter like x times y to something.
It can be, but like, okay, this is actually the answer for the previous question about f and v, so it not have to be a connection between them, and it is just a hint, like You can start from nowhere. Maybe there is another function. Maybe there is like everything. So in this way, Strobel told us, let's do it like this. Okay. Okay, solution. So now we have the fixed point 0, right? First. And okay, let's start. Assume that we have this function, okay? So v dot will be mx by m minus 1x dot plus a n y to the n minus 1 y dot, right? Okay, we'll put it inside. We are getting m x to the minus 2m minus 1 minus x plus 2y third minus 2y fourth plus a n y n minus 1 minus x minus y plus xy. This is mx by n plus 2mx m minus 1 y third minus 2mx m minus 1 y to the fourth plus a n minus a n x y n minus 1 minus a n y to the n plus a n x y to the n. Right? We want that v dot where it is will be lower than 0, right? Okay, so let's choose m and a, right? What I did wrong, here is minus. Plus, minus. Okay, great. Let's try to cancel things. Okay, so we can choose m to be 2 and n to be 4. Then we have this, and we have this. Right? Which cancel. Okay, so v dot is minus 2x squared plus, let's make it clear, 4x y third minus 4x y fourth plus minus a 4x y third minus a 4y fourth plus a 4x y to the fourth. So let's choose also a equal 1, right? So we can just erase that, and this cancel with this and this with that. Therefore, we stay with minus 2x squared minus 4y to the fourth. This is positive, minus minus, so it is always lower than 0, right? Cool. Okay, so we find the first condition, right, for Lyapunov, but there is also the second one. So what is the second one? Da-da-da-da-dam. Okay, return to v. V of xy is x squared plus y to the fourth. And we want xy will be lower than 0, and at the fixed point it will be 0. Did it happen? Yes. So we did the Lyapunov proof, and there are no periodic solutions. Right. Okay. And Okay. Last question. Show that the system x dot is x minus y minus x third and y dot is x plus y minus y third. And show that this system has periodic solution. That the system has periodic solution. Okay, so how we are going to do that? First, let's look at the lines where x dot equals 0 and y dot equals 0. This will happen for x equal y, okay, y equal x minus x third, and this will happen when x equal y third minus y. Right? So it looks like this is x and this is y. We'll have something like this. Okay, this is the 0 and this is the 0 point. Okay? Okay, in this area we have this. In this area we have that. Here we have this, and here we have this. Okay, that means that the arrows here are here, that means that, and that. Okay? Okay, we want to prove that there is a periodic solution. Okay, we want to use a Poincaré-Benedictson proof. Okay, that for that there is some periodic solution. Is it clear why there is a closed loop, or I will do it slow? Okay. So let's look at this. We have okay. Let's say that we start here, okay, in some point a dot a, HCK. Okay? In this area we have x dot lower than 0, right? And also here. That means that this point will go until here, right? Will go this direction. Okay? Right. It will hit this line, right? And here we have y dot is lower than 0, and also here y dot lower than 0. That means that it will go down, right, until it will hit this point. Okay, in this point, here we had x dot lower than 0, and here x dot lower than 0. That means it will go right, until it will hit this point. Okay, and now again we have y dot lower than 0, and here y dot lower than 0, and it will return to this point. Why it will do exactly this, we can do it from the from the equations, but we have 3 minutes. So you can believe me and do it by home or maybe later. Okay, so
it has to be x, right?
What?
The middle one.
The middle, this?
To the right. The condition that y is bigger, it's x, right?
No, x dot is lower than x.
Ah, okay, yes.
Okay. So we have the closed loop, right? And now we want okay, we want to see that there is no a stable fixed point, okay, for the reason that there will be an orbit, okay, a closed orbit. So we know that we have a critical point at 0, 0, right? So let's look on the Jacobian. The Jacobian is 1 minus 3x squared minus 1, 1, 1 minus 3y squared. So at 0, 0, we get 1 minus 1, 1, 1. That means tau equal 2 and delta equal also 2. That means that we have unstable spiral. Okay, so we don't have a stable fixed point. Okay, let's do it in some different color. The system will do something like this. Okay, but we saw that there is some area R that we start here and we are done going out. Okay, even though that this is unstable. Okay, so that means that somewhere in this area we have some closed orbit. That's all.
What the last sentence?
That we have some closed orbit. Closed loop.
And it doesn't contain the fixed point, right? It cannot.
Yes. The fixed point. Okay, imagine that we have this, but we have a stable spiral. That don't mean that we have some closed loop. Maybe we can do again like this, but we are going to the fixed point. To the point, not to a circle.
Right. The reason is that we cannot have the close if we contain the fixed point, right? That's what I'm asking.
Yes, yes.
We must leave out the fixed point of the contour of the curve.
No, maybe I don't know how. I mean, I can draw it by the computer, but so I don't know now. But maybe the close-up will be here, and the fixed point is in the middle.
Then we cannot use the theorem, right?
When?
The theorem. Like we need to leave out the fixed point, or no? In order to
You don't have to. But actually, you can say, okay, let's take this and go out this. So we have all this area without the fixed point.
Closed orbit יכול להיות unstable spiral.
No, it is spiral. It is not an orbit.
עכשיו שיוצא unstable spiral.
Unstable for the critical point 0, 0.
כלומר זה מתכנס זה מתכנס ל-0-0?
No, it is go out from the.
זה לא closed orbit.
No. We saw that there is no a fixed point at 0, 0, but still we have some area that if we will start there, we will stay inside this area. That means that there is a closed loop.
זה נקרא ליפוין of stable?
No, this is the second one. Wait.
Okay.
No, something we
נקרא neutrally stable?
Wait. Poincaré-Benedictson. Você Poincaré? So, yes, Poincaré-Benedictson. this is how it works. Okay, good night.